Um, okay, welcome back everybody to Probability and Analysis webinar. Today we have Alexandros Eskenazis from Cambridge University who will speak about metric influence inequalities. Please, Alex.
Okay, thank you, Pato. So everything I'm going to say is joint work with Dario Cordero. Now I'm looking at the audience. I'm seeing many people that really know too much about the subject and in general. So this was meant to be a talk for non-experts. So I hope it won't disappoint. In particular, there aren't going to be any proofs. So if you came here to see a proof, just read the paper or ask me later. So let me start with some things which we are going to need from Boolean analysis and Banach space theory, which are two things that kind of go together, but kind of unexpectedly. So in this talk, we'll be dealing with functions defined in -1 to the n, which is the discrete hypercube, and have values either in a Banach space or more generally in a metric space. And we're going to try to prove some inequalities and do some analysis for such functions. So the first thing is that, for a function with values in the Banach space, we can define its partial derivative. So the partial derivative of f at a point epsilon, where epsilon is the vertex of the cube, is that, you stand at the point epsilon, you move along the edge on the ith direction, and you see how much your function changed, and you're dividing by 2. Okay? That's the definition of the ith derivative. And the other term, which is going to be somehow implicitly important in a lot of the things that I'm going to discuss, is the hit flow on the Hamming cube. So the hit flow PT acts on a function f by the following formula. So PTF at the point epsilon is the expectation with respect to a random vector xi of t of f at the point epsilon pointwise product xi of t. So this is the vector epsilon1, xi1 of t, epsilon2, xi2 of t, etc. Where now the coordinates of xi of t are independent, and each of them has this distribution here. So xi of t is 1 with probability 1 plus e to the minus t divided by 2, and -1 with the remaining probability. So for instance, for t equals to 0, all of the xi's of t are deterministic and equal, in which case p0 of f is simply f pointwise. And for t equals to infinity, the xi's are uniformly distributed, so p infinity is the average of f. And one basic tool that we have in analysis of Boolean functions is the Poincare inequality on the Hamming cube, or also known as the Efronstein inequality, depending on somehow the community, which asserts that for a function on the Hamming cube and values in the complex plane or the real line, so the two will be exchangeable for this talk, it doesn't make a difference, the variance is bounded above by the sum of the L2 norms squared of the partial derivatives, which is nothing but the length of the gradient. By the way, the only measure on the Hamming cube for this talk is going to be the uniform measure, so there aren't going to be any surprises. And okay, just as a reminder, as many of you know, this is equivalent to the exponential decay of the variance of PTF. So these were the preliminaries when it comes to analysis of Boolean functions. So now let me say a word about Banach spaces, and let me start from the obvious point, which is Hilbert space. So in Hilbert space, we have the parallelogram identity, which says that if you have any n points, x1 up to xn, and you try to evaluate the expectation of the norm squared of some epsilon I xi, where now the epsilon i's are independent plus minus 1 Bernoulli variables, then you can write this as the expectation of the inner product of this vector with itself, and basically use multilinearity so that what shows up is the expectations of epsilon I, epsilon j. And because of independence, the only terms which survive in this sum are the I equals j ones. And therefore, what he gets is the expectation of this sum squared is the sum of the vectors, of the norms of the vectors squared. And now in some of the classical local theory of Banach spaces from the 70s, people were really investigating one-sided relaxations of this property. And one of the two inequalities that you can define is the notion of Rademacher type. So we say that a Banach space has Rademacher type P if there exists some universal constant T, so that as before, for every n, and for every n vectors in my space, if we look at the expectation of this Rademacher sum, of the norm of the Rademacher sum raised to the power P, this is bounded above by this universal constant, which we're not going to think about because it does not depend on m and the choice of vectors, times the sum of the norms of the vectors to the power p. So this is the notion of Rademacher type. It has some fairly obvious properties. First of all, it only depends on the finite dimensional structure of the space. So it's what we call a local property. And secondly, it's isomorphism invariant. So if we have two isomorphic norms on a Banach space, and of course, one has Rademacher type P, even only if the other has. So some probably equally obvious or slightly less obvious observations are that, first of all, the parameter, the type parameter of a space is always between 1 and 2. So first of all, in the case P equals 1 is simply the triangle inequality. So this does not include any additional structure. And because for a line, just for a one-dimensional space, this inequality becomes an equality for P equals 2, we immediately get that P cannot be any number that's larger than 2. So it's a parameter that's always between 1 and 2. What's slightly less obvious and follows from Kahan's inequality is that the left-hand side of the inequality is in fact independent of P up to a universal constant factor. So the LP norms of Rademacher sums are equivalent to the LQ norms, and therefore the only real dependence on P lies on the right-hand side. And this means in particular that if you have a space that has type 1.7, it also has type 1.3. So type is an increasing property, and type 2 is the most delicate somehow, is the best type you can have. Type 1 is simply trivial. It's true for everyone. And just to have a concrete example, if you have an LR space where R is just finite, then it has type which is the minimum of R and 2. So L1.5 has type 1.5, L2 has type 2, L4 has type 2. All right, so these are the basic definitions for type. I'm sure many of you have seen them. What I think is an interesting question that should be addressed in every talk about type is, why should we care? Why did people investigate it? Where is it coming from? And if you basically go back to the books, the first thing you're going to read is that it captures deep structure for vector valued random variables. For instance, you get rates of convergence for vector valued limit theorems and so on. So basically the whole Ledoux-Lagrange book, or at least half of it, is about Rademacher type and its applications in probability in Banach spaces. From the point of view of this talk, we're going to be interested in something slightly different, which is a geometric application of type. So type is an obstruction to isomorphic embeddings. And let me explain what I mean by an example. So suppose we have a norm space which has Rademacher type 2, and the constant is just a universal constant that I'm not going to care about. And consider now a number P which is smaller than 2, so in the regime of worse Rademacher type, and a linear operator from LPM inside your norm space X. And simply apply the Rademacher type inequality for the vectors in X, which are the images of the basis vectors in Rn. LPN, by the way, I should say, is Rn with the LP norm for this talk. So we get this inequality over here, which is simply the Rademacher type inequality for the images of the basis vectors. But now suppose that we know that T is a bounded operator. Suppose that we know that it's bounded and its inverse is also bounded. Then we can definitely bound the right-hand side as we do here. So we can bound each T of EI by the operator norm of T times the norm of EI in LPN. And of course, the norm of EI is just 1. So the right-hand side of this inequality is bound above by the operator norm of T squared times N. Similarly, if you try to do this for the lower bound, first of all, you're going to use linearity. So the sum of epsilon I T of EI is T of the weighted sum. And this is bounded below by 1 over the norm of T inverse squared times the expectation of this Rademacher sum now in LPN. And the norm of this quantity in LPN for every choice of epsilons is simply n to the 1 over P. So we get that the left-hand side of the inequality we have above is bounded below by n to the P 2 over P times the norm of T inverse divided by the norm of T inverse squared. And now you can rearrange the inequality, and what you get is that the distortion of this operator, which is simply the norm of T times the norm of T inverse, is bounded below by n to this explicit power, 1 over P minus 1 over 2, which is a positive number. So what we get basically is that the fact that your space has Rademacher type 2 implies a lower bound, which by the way is clearly sharp, to how well you can embed isomorphically the space LPN inside your norm space. Okay, so in that sense, Rademacher type serves as an invariant. So let me move on to the next thing, which is nonlinear things. So this, all of this talk, but a lot of the talk about this subject implicitly belong in a research program in metric geometry that's called the Riebe program. So this was formalized by Bauguin in 1986, but somehow the motivation behind it was a rigidity theorem of Martin Riebe from a decade earlier. And the message of Bourdieu's program, the way he stated it, is that properties like Rademacher type, which are isomorphic and local, can be rephrased only in terms of distances between points. So even though Rademacher type in its definition has this, this weighted sum and so on, so it appears as a very linear property, it's in fact somehow a metric property in disguise. And a metric version of Rademacher type was already defined before Riebe's theorem was proved by Per Enflo in the late 60s. And the definition now is as follows. So we say now that a metric space, not a Banach space, has Enflo type P if for every n and for every function from the Hamming cube inside my metric space, we have the following inequality for this function. So the expected distance between f at one point and f at its antipodal point to the power p is bounded above by this universal constant again, for which we will not care about, times the sum as I goes from 1 to n as the expected pth power of the distance along the ith edge. So this should be really reminiscent of what was happening in type. We had this big Rademacher, and we said that we're comparing each of the increments. And here again, we have a function defined on the whole Hamming cube, and we want to compare the lengths of diagonals to the lengths along edges. And there are some fairly trivial things to say about Enflo type as well. First of all, Enflo type 1 is simply the triangle inequality, because you can just travel from one point to its antipodal just by basically any path and then average, and that's it. So Enflo type 1 is not an interesting property of a metric space. Moreover, if your metric space is in fact linear, then Enflo type P clearly implies Rademacher type P. And the reason that's true is that you can simply choose a linear function. And before somehow moving on and telling you more things about Enflo type, which are more recent and extremely interesting, let me address the previous question, which is why should we care? Okay, so why did Enflo already care, and why do people care about this in the 21st century somehow? Again, the point of view of this talk is going to be about embeddings. So remember, Rademacher type said that if you have this good property, then you cannot find a copy of LP for P, say, smaller than 2, Rademacher type 2, inside your Banach space. Now, Enflo type basically serves the same purpose, but instead of LP, you're talking about simply the discrete metric space, which is the Hamming cube equipped with the P distance. So suppose that your space M has Enflo type 2, and that F is a function defined in the Hamming cube with the P distance, which is a bi-Lipschitz embedding inside your metric space. Okay, and now we're going to do exactly the same thing. So we are going to write the Enflo type inequality, here it is, and we're going to bound both the right-hand side and the left-hand side by using the bi-Lipschitz condition for the function F. So for the upper bound, this is very easy because you can bound the expected distance between this point and this point by the Lipschitz norm of F times the expected distance on the Hamming cube between epsilon and its adjacent point, but this distance is always 1. So the upper bound is always going to be n times the norm of F. For the lower bound, you can basically do the same thing. You can bound it below by 1 over the Lipschitz norm of F inverse squared times the expected distance between two antipodal points. But remember that we're measuring the P norm, so this is n to the 1 over P, and therefore you're squaring it, you're getting exactly the same bound. And again, you can combine the above and deduce that the distortion of F, which was a bi-Lipschitz embedding, is bounded below by n to the, n to the 1 over P minus 1 over 2. Okay, so we want the exponent to be positive, P is smaller than 2. So we get exactly the same bound, but the thing is that instead of saying that we cannot find a copy of the huge linear space inside our our metric space or our norm, we cannot even find a copy of the smaller Hamming cube, and we have to pay exactly the same distortion factor. Okay. So the message is exactly that it's we have the same form of incompatibility, but very strongly, we have to pay exactly the factor in order to embed just this discrete subset of LP. Okay. And it's very natural to ask, how do these two compare? And what is even meant by somehow metric properties in disguise in Bourdieu's sense? Now, the first part of any investigation in the RIBA program is to say that I'm going to take a standard linear property, something which I think I understand in the linear world, and translate it into the metric world, in the sense that the property is going to be equivalent for the class of linear spaces to a metric property. And this was a long-standing problem of N-flow that was resolved last year in a paper that I'm sure most people here know. This was a big breakthrough of an Israeli Van Handel and Holberg, who showed that in fact M-flow type and Rademacher type are equivalent properties for Banach spaces. And the way this was done, I mean, I'm not going to talk about the proof at all, but somehow the basic thing I would say for the case of Rademacher type 2 is that you basically have an exact copy of the Poincare inequality for spaces with type 2. So the left-hand side in this inequality here, which is exactly the vector value that analog of the variance, is bounded above by exactly what you would have in the Efronstein. And this, of course, automatically implies the metric property, which is M-flow type as well, just by a triangle inequality on the left side. So this is basically the first part in the RIBA program, to say that, okay, we've somehow done the translation from linear to nonlinear. The second part, which is equally important, is to deduce somehow metric properties and understand the metric structure of spaces that satisfy the nonlinear property and are not norm space, just metric spaces. So this was kind of the background. I think this is a very good example to explain this circle of ideas. And now let me move on to what is actually the subject of this talk, which is influences and Talleyrand symbol. And I'm going to start with a little bit of motivation again, something that probably everybody knows. So if we have a Boolean function f, by Boolean, I'm going to mean that its values are -1 and 1. The ith influence, the way we're thinking about Boolean functions, everybody knows again, but okay, is as voting system. So basically we have n voters and we have, two possible outcomes, -1 and 1. So every person votes and the votes are recorded as a string of -1s and 1s. And you have a voting system f, which at the end tells you who won. So in this formalization of a Boolean function, the influence of the ith voter is the probability that it's going to be the ith voter that will determine the result. This means that you sample uniformly at random the votes of the remaining n-1 voters, and then you ask what's the probability that actually the ith voter is going to be the one that's going to determine the outcome of the election. So this is the ith influence in the terminology of analysis of Boolean functions, and in the analytic terminology, this is nothing else than the L2 norm squared of the ith partial derivative, or because it's Boolean, the L1 norm of the partial derivative. And in this terminology, the Poincare inequality exactly says that the variance is bounded above by the sum of the influences. And in particular, it's even further bounded by n times the maximum influence. So the Poincare inequality tells you that there always exists one voter whose influence is bounded below by the variance divided by n. Now, this bound is famously suboptimal, and is a celebrated theorem of KKL and Lineal from 1998, which says that in fact, for every Boolean function, the maximum influence is bounded below up to a universal constant by log n over n times the variance. And this is known to be short. So log n over n is the best you can hope for, and basically it says that no matter what your voting system is, there exists one voter who somehow has a larger contribution that one would anticipate. So this is the KKL theorem, and one main contribution in their paper is that they introduced Fourier analytic methods in analysis of Boolean functions via the use of hypercontractivity and the Hamming cube. And a few years after that, Talleyrand actually exploited an analog of hypercontractivity to deduce a strengthening of KKL, which is not just true for Boolean functions, but it's in fact an inequality for real valued functions. So it's now a more analytic state. And his inequality reads as follows. I'm gonna state in the stronger possible form because I think that's the best way for this talk. It says that if you have any function from the Hamming cube into the real line, then the variance is bounded up to a universal constant by the sum of the L2 log L to the -1 norms squared. So Poincare tells you that's bound by the L2 norms squared, and L2 log L to the -1 is an Orlich norm, which is just slightly smaller than L2. So for those of you who don't know what an Orlich norm is, it doesn't really matter. It's bigger than any LP for P smaller than 2, but it's still slightly smaller than L2. So it shows that you have a tiny improvement there, you win by this log. And then by means of elementary calculus, you can actually show this bound over here, which says that in fact this L2 log L to the -1 norm is bounded above by the L2 norm squared divided by 1 plus log of this ratio of the L2 over L1 norm. So in particular, if your function f does not have a constant absolute value, if the ith derivative of f does not have a constant absolute value, which means that basically DIF L2 and L1 are going to be the same, then you get an asymptotic improvement of the Poincare inequality. So this is the more familiar form of Talleyrand's inequality. For this talk, we're not going to discuss applications for influences, so I'd rather stick with a stronger notation, and there's going to be a reason for that later. And again, just to show you the connection with KKL, if your function is Boolean, then the L2 norm is just the square root of the L1 norm in the derivative, so it's just the square root of the influence. So Talleyrand reads that the variance is bounded above by the sum over I of this function of the influence. And then, you just bound it again by the maximum and you get exactly KKL. So this log in the denominator is exactly what wins you this log n in KKL, in the KKL theorem. But this time through a completely analytic statement that had to do with Orlich norms. Are there any questions, by the way? You should feel completely free to interrupt. I forgot to say. So probably everybody saw where I'm going with this. The natural question from the point of view of the theory of vector valued harmonic analysis is, are there versions of Talleyrand's inequality for functions with values in norm spaces, and more ambitiously, are there versions for functions with values in metric spaces? And somehow this could just be a curiosity. What I hope to convince you is that this is beyond a curiosity and it's actually useful for something. So this is going to be the main subject of this talk. So there exists, and I'm going to give a definition now, which is the following. Fix a parameter P and fix psi from R plus to R plus a Young function. By Young function, I mean basically an increasing convex function for which you can define the corresponding Orlich norm. So just to keep in mind, it's always going to be for this talk, this function T to the P times log to the minus some power, which is what gives the Orlich norm we had before, but we can of course define it for an abstract Young function. So we're going to say that the metric space now has the Lagrange type with these two parameters, P, which is the exponent, and psi, which is this Orlich function. If again there exists a universal constant such that for every n, and for every function on the Hamming cube with values in my metric space, I have this inequality over here. Now, let's just read it slightly carefully because there are a few differences from emplotype. First of all, on the left-hand side, we have the expected distance between f of epsilon and f of delta raised to the power p, where epsilon and delta are two independently chosen random vectors in the Hamming cube. Now, this could just as easily have been the definition of emplotype, and it wouldn't change any of the results. I think this is slightly more canonical than doing epsilon minus epsilon. So if I had a choice, this would be actually the definition for emplotype, but anyway, now we had a choice, so we defined it like this. But it shouldn't matter. The left-hand sides are the same. Now, on the right-hand side, we have again this universal constant times the sum of the L psi norm of this derivative di raised to the power p, where now di is the distance in my metric space between f at epsilon and f at the point where I flip the ith coordinate. So di of f is a scalar valued function, and I'm taking the psi norm of this quantity. Okay, and of course I should probably say, let me just maybe write it, for a norm space, DIF at epsilon is simply the norm of DIF at epsilon, which is the notion of a partial derivative that we defined before, but I cannot define the difference in a metric space, so that's a substitute. Does this make sense? So again, to see how this extends M-flow-type, you should think of M-flow-type as being exactly this inequality, but for the function being the Young function just being t to the p. And again, there's a small distinction on the left-hand side, but this shouldn't matter too much. It doesn't matter for any of the application. And again, let's go back to the most important question, which is why should we care? So we have a new invariant. It's very clearly a by-Lifshitz invariant. So one can ask, did we win something? Is there a new class of metric spaces which we can understand whether it's compatible with a metric or not by looking at this invariant? And the answer is actually yes. So I think that's somehow one of the main things here. So Talleyrand type, in fact, implies the non-immutability, not of the Hamming cube itself. Of course, it implies also the non-immutability of the Hamming cube, but it implies the non-immutability of quotients of the Hamming cube. And let me now go over the construction of quotients for you. So now I'm just going to restrict to the Hamming cube with the usual L1 metric, just for simplicity. It doesn't make a difference. So Cn is going to be the metric space, which is -1 to the n with the L1 metric, maybe normalized by 1/2. And now suppose that R is an equivalence relation in the Hamming cube. What this means is just the very basic notation for saying that we have an arbitrary partition of the Hamming cube into pieces. Okay, these are just the atoms of the equivalence relation. So my the metric which I'm going to try to embed is the quotient space, which is just the atoms of the partition. Okay, and if I have two equivalence classes, so two pieces of the partition, like this one here and this one here, then I can define a weight between those two, which is going to be the minimum distance between one and the other. Now, unfortunately, this is not a metric. This does not satisfy the triangle inequality. But nevertheless, the quotient space equipped with this is a weighted graph, and therefore we can define a metric on the quotient space based on these weights. So this means that, you know, the distance between one point and any other is going to be simply the shortest path, where the length of the path is just going to be summing up the corresponding weights. And I'm going to denote by this notation over here, so this row indexed by the quotient, which now they say is not a great notation with my handwriting, but okay, the shortest path metric on the space of equivalence classes, so on the atoms of the partition. And here's the fact. Talleyrand type, in fact, gives you a lower bound for the distortion of these spaces. And somehow deriving the lower bound is completely trivial. Whatever originality exists here is by where this class of spaces comes from. So the statement is the following. Again, I'm going to restrict myself to exponent 2. So if you have a metric space which has Talleyrand type 2, psi is this arbitrary Young function, then for every quotient space, here the function is not defined on Cn, it's defined on Cn over R, which means that basically it's a function on Cn that's constant on each piece of the partition. Then the distortion is bounded below by this quantity here. And now this quantity has two mysterious parameters, this A2, which I want you to forget just for a minute. And here on the denominator, this function psi, which is the corresponding Orlic function, shows up. Okay, so now let's just go over it slightly more carefully. So A2 for any reasonable partition is simply going to be equal to n. So it's the expected distance between any 2 points on the Hamming cube on the metric induced by the partition. So if your partition is not extremely crude, this is going to be equal to n. And I just want you to think about it as if it were n from now on. What we have in the denominator is the function psi inverse applied to this quantity, sigma n of dir to the -1. So let's just explain what this is. Now, dir is what I'm going to call the ith boundary of the partition. So it's exactly those vertices on the Hamming cube whose ith neighbor is not on the same part of the partition. So they're not, they're on different clusters. And sigma n is the uniform measure. So what's happening here is that you have the inverse of the uniform measure of the ith boundaries. And how should this be read? Somehow, this is a complicated formula, but what's the message? The message is that very often, for instance, in Talleyrand's inequality, we can get, say, the standard Poincare inequality for which the Young function was t squared, and improve it to a Young function that's slightly smaller, t squared divided by log t, or something like that. Okay, so if you look at this quantity here, if you have a function psi that's small, then psi inverse is large, and therefore psi inverse to the -2 is small. But this is on the denominator, so the right-hand side becomes large. So in principle, if your function psi becomes a bit smaller, this says that the distortion of this metric space automatically has to become larger. And I want us to read this also in a slightly different way, by analogy with what's happening in the KKL theorem. So these measures of the ith boundary are really exactly, are playing the role of the influence in this setting. Okay, so KKL is usually read in the following way. If you have a function which is balanced or its variance is 1 or whatever, then there exists one large influence. But let's somehow insist on the contrapositive of that. If you have a function, KKL says that if you have a function, all of whose influences are very, very small, then it definitely values one of the two candidates on the voting scheme more than the other, in the sense that the variance is very close to 0. Okay, and what's happening in this inequality is really of the same nature. So here we have the statement that if all the geometric influences, which are the measures of the boundaries, are very, very small, then my metric space, this quotient, is increasingly incompatible with the geometry of the space which has the good property, which has Talleyrand type, whatever. Okay, so here there's a trade-off. Basically, you are trying to make your boundaries very small to get larger distortion, but you need to be careful because if you make them too small, this quantity A2, which is basically morally always equal to 1, is going to completely collapse. So you want to play this game between these two parameters. So is it clear where somehow the qualitative improvement is coming from? All right, good. Okay, so this is somehow why these objects are useful, or anyway, one reason for which we believe they're useful. And let's just go to the also important thing, which is what can we prove? Okay. The first thing, okay, let me set up some notation first. I'm going to denote always from now on by psi p comma delta, this function which is t to the p divided by log to the power delta of e plus t. Now, I'm just saying always for large t, because this is not convex near 0, and you just, only the behavior at infinity matters when you're talking about. So let's just have this function, which is t to the p divided by log to the power delta. The first thing which we can prove is something which, at least formally, is an improvement of the theorem for M-flow type, which says that if you have a norm space with Rademacher type P, then, and P is greater than 1, and that's kind of important, then X actually has the Lagrange type, which is psi P, comma, a 1 minus epsilon power of the log. So just to remind you, if we put a power 0 here in the log, this is simply M-flow type. Okay, so basically there is this improvement. Now this is only formally an improvement because in fact this is exactly what follows from the proof. It's a slight modification. You somehow, you have one additional use of hyperconductivity, but it's not, there is no additional idea. But there is this one slightly delicate issue that somehow looking at the scalar value inequality, which we believe that there should be a power -1 to the log. Whereas here we have this, -1 plus epsilon for every epsilon. And in fact, this seems, at least to the extent which I know when I've discussed with people, kind of inherent to this argument. So a divergent integral dt over t shows up, which was never a problem, in the case of M-flow type. But here you are taking, you're doing a more delicate thing. There's an additional singularity, and this simply shows up. And I currently have no idea whether it's necessary or not, but at least I'm quite convinced that from the one needs some additional idea from that argument to prove it. So what we could do, and in fact, it predated at least the posting of the paper on amplotype, is that we could prove the optimal result under a slightly stronger assumption. And the assumption is going to be that of martingale type. So we say that the Banach space, this is a definition due to Pizier from the mid-70s, that's also extremely influential for other reasons. A Banach space has martingale type P if again there exists a universal constant, such that for every x-valued martingale, the expected pth power of mn minus m0 is bounded above by this universal constant to the p times the sum of the expected pth power of the martingale differences. So remark number one, this thing makes sense in the scalar value world because in Hilbert space or in the real line, martingale differences are orthogonal. And therefore we have simply, again, by the parallelogram identity, this is an identity for p equals 2 in Hilbert space. The other thing which is obvious is that martingale type is stronger than Rademacher type. And that's because you can just define a martingale to be a Rademacher sum where you reveal one coordinate at a time. But this a priori seems something much, much stronger than Rademacher type. Well, it turns out that, as is often the case in Banach space theory, yes, it is stronger, but somehow finding an example is not at all trivial. And in fact, to this day, we basically know 2 or 3 examples, depending on what you consider. But there exists, there's a deep theorem of James from 1978, which says that there exists a Banach space of Rademacher type 2, so it has the best possible Rademacher type, but it simply has no martingale type. Besides the trivial on p equals 1, I should also say p equals 1 is just a triangle. So the two notions indeed are different, but sort of for any classical space that you would most probably meet, they're absolutely the same. So our second theorem is that if instead of the necessary Rademacher type 2 assumption, we assume, or Rademacher type p, okay, I guess, we assume that the space has martingale type p, then we get actually the optimal exponent in the Talleyrand type inequality. So this usage of martingales kind of allows us to deal with the singularity there. And I'm not going to say much about the proof. It's basically this window over here. So why does martingale type come in? So the first thing that you do is that you write f minus its expectation as basically an integral along the heat flow. So you write as an integral of the time derivative of PTF. And then there exists a very nice construction due to Eldon and Gross from a couple of years ago, which is a martingale. I should have said that this is empty. It's a continuous time martingale. It's actually a jump process. So that for every fixed time t, mt has the same distribution as PTF. And the quite amazing thing is that the increments actually behave exactly like a sum of independent random variables. So in fact, you can somehow run the martingale type argument along this flow. You need to estimate several things carefully, but you can actually make it work. We had the second proof of this theorem in our paper. The second proof is actually analytic. The starting point is the semigroup approach of Ivanishvili, Van Handel-Wahlberg, but at the punchline, you had to somehow deal with the singularity. And the way to deal with the singularity there was vector-valued Liu-Palestine theory. So in fact, there we used a recent theorem of Kwan-Hua Shu, who showed that under martingale type 2, you have somehow the perfect one-sided Liu-Palestine theory that you want, and it does indeed follow. But you need some Fourier analytic tool apparently to deal with that singularity there. And this stochastic proof, relying on this process of Eldon and Gross, has some advantages. It gives better constants. It's somehow more self-contained. It's if you are to read one thing, you recommend this. All right, and let me close by just insisting a little bit on the lower bounds on distortion. So if X has martingale type 2, then we know now that it has Talleyrand type psi 2, 1. And therefore, we have this lower bound here by for the distortion of the bi-Lipschitz embedding of a quotient. So you see here on the denominator, we have this psi inverse, where psi is now the explicit function t divided by log t. Whereas if one only knew the M-flow type of the space, which we already knew, of course, the bound that you would get is simply this. So there exists one additional logarithmic improvement, which is genuinely coming from the presence of influences. Are there any questions about this? Let me say a few words, mainly open problems, but things we've tried and I think are extremely interesting. The main question, okay, one of the main questions, okay, now you have a reasonable understanding of how the metric invariant behaves for norms, but the whole reason you define a metric invariant is to go beyond norms. So can we evaluate the Talleyrand type of any interesting class of nonlinear spaces? And somehow for me, the class of spaces for which I would start is that of spaces with curvature. So, you know, here in the picture, I'm sorry for my artistic skills, but in the picture you have on the left a space of non-positive curvature, something like the hyperbolic plane. In the center you have something like you know, the plane basically, and on the right you have something like a sphere. So let me tell you the definitions of a metric space with curvature in the sense of Alexandrov. So we say that a metric space is an Alexandrov space of non-positive or non-negative curvature if for every 4 points as above, so x, y, z is a triangle in my space, and M is a metric midpoint of x and y, meaning that the distance from x to M is the same as the distance from M to y is 1/2 times the distance from x to y. We have that the distance from z to the midpoint squared is bounded above or below by whatever it would be in the case of the Euclidean plane. So in the case, say, of the blue inequality, which is non-positive curvature, what I'm saying is that in the picture on the left, the distance from z to m should be bounded above by the distance from z to m in the picture in the middle. So this is, again, for complete geodesic metric spaces, the notion of Alexandrov non-positive and non-negative curvature. And here, of course, we make absolutely no smoothness assumption. There's no manifold structure and so on. Now, it's well known, one of the two implications is actually already due to M-flow, that Alexandrov spaces of both non-positive and non-negative curvature actually have M-flow type 2, even with constant 1. So that's something that's completely clear. It's something that you can prove by induction, both of those things. So the question is, can we actually, for these very classical spaces, prove the refinement, which is now Talleyrand type? And I should say, actually, this was kind of implicit in what I said, that somehow the key to a lot of these inequalities is the use of hypercontractivity. And one really needs to think about what hypercontractivity is when you're not talking about norm spaces. So the conjecture which I have is that in the case of non-positive curvature, we have exactly the same Talleyrand type as in Hilbert space, whereas in the case of non-negative curvature, we do not. And I'm sure that actually the second thing is reasonably easy to prove. You know, there's something that we thought after the paper and we didn't try, but I'm sure the second thing is fairly clear. There's an easy, you know, an easy candidate for a counterexample. And unfortunately, we could not prove this for an arbitrary space of non-positive curvature, but we could prove this at least for certain interesting classes, up to, again, this power epsilon in the exponent of the log. So we could prove this for Gromov hyperbolic groups, which is, well, hyperbolic groups with some strong notion of non-positive curvature. It doesn't really matter what this is. And more somehow, a more tractable example is Riemannian manifolds, which are finite dimensional, and their curvature is between two universal negative constants. Okay, curvature between -1 and 4. So this is the notion of pinch negative curvature. So for those spaces, we can actually prove that we have the correct Talleyrand type up to this epsilon in the exponent. But unfortunately, this is, I would say, some of the very few examples which we currently know. And I think that getting the case of non-positive curvature in general would be quite interesting. So that's what I wanted to say. Let me tell you a few more things that are in the paper, and kind of, I didn't say anything technical, and I didn't speak also about the more harmonic analytic aspects. So some things we didn't cover are what we call L1-LP inequalities. Now, because of the quotient, L2 norm over L1 norm, Lagrange inequality is often called the L1-L2 inequality. Now, we also have some L1-LP inequalities, where you say that the LP norm of F minus expectation is bound above by an Orlich norm of the gradient, which is slightly better than the LP norm. And you can get, the correct exponents and so on. There is a quite bizarre L1 inequality, which I don't completely understand, and the proof is not what you would expect. So I'd be also very happy to see a more normal proof, which says that F minus expectation is bounded above by a sum of the, the L1 log L to the -1 norms, the derivatives, which is kind of, to me, it doesn't seem at all related to the L1 Poincare inequality. It's somehow in a different direction improvement of the triangle inequality. We had some bounds for delta to the -alpha inside somehow the optimal Orlich spaces, which is basically the optimal vector valued version of the theorem of Bakri and Mayer from the 80s. And we also have a vector valued version of the holomorphic multiply theorem of Mayer. Again, with the optimal assumptions on the space and so on. So yeah, that's it. Thank you very much.
Thank you very much, Alex, for the beautiful talk. Does anybody have any questions? Please feel free to unmute yourself.
I have a question. So you use this Young function, but if you have this Young function, usually people use Luxembourg norm. And what you wrote at the very beginning, like Talleyrand 1994 inequality, you interpret it as an inequality with Luxembourg norm, but formally it's probably corollary of that, right? Because what is written is not Luxembourg norm.
So what's written in Talleyrand's paper?
Talleyrand inequality, right? It doesn't look like Luxembourg norm, right?
So he actually has a section where he proves a stronger inequality with the Luxembourg norm.
I see, and that's a corollary of. Oh, I see.
So Talleyrand's paper is written in a very interesting way that he starts from the much easier things and eventually he says, but this is the real inequality that I'm going to prove. So but this is actually proven there. But but that's not what people usually call the influence inequality. It was just slightly more convenient because, for instance, you see, if you want to define a bi-Lipschitz invariant, the moment you put the Orlich norm, it's completely obvious that it's a bi-Lipschitz invariant. But if you have this quotient between L2 and L1 or something, it's not just as it's not as obvious.
I see. So he really uses.
So he really proves that.
Yeah. Okay.
Any other questions? I have a question, Alex. So martingale type implies the Lagrange type with the epsilon equals 0. Are there any converse implications?
Not that I not that I know of, and I'm not even sure what to believe about this. I seriously doubt that Talleyrand type. Oh, I'm on record now. Okay, I seriously doubt that Talleyrand type implies martingale type. I don't know what the right answer will. I don't see any conceptual reason for that to be true. But maybe. I mean, it could be that the answer is simply somewhere in between, and there is no very natural class of spaces for which that's true. But the problem with this and with many of those issues actually is that it's very hard to deal with the spaces in between. Anyone reasonable and very motivated would take the James space and just try hard to prove the inequality on the James space. But I don't know if anyone would actually do that. And if it's even possible, there are complicated spaces they can't resolve. So yeah, I don't know what the truth is in that in the correct class.
But okay, let me ask another question. So Rademacher type 2 implies Talleyrand with epsilon greater than 0. And do you think it will not imply with epsilon equals 0, and the best candidate would be to try James space?
Yeah, I have no guess. I have no guess. Maybe it will. So okay, because we discussed this a little bit as well. So it seems that from this argument, one needs something additional to deal with the singularity. Maybe you can just do it with just a smarter use of the tools that we already have for Rademacher type, but I don't immediately see it. It's basically, the moment you flow in the t direction and you use as your martingale PT, which can be lifted up to martingale, then basically, there are no independencies there, and Rademacher type is all about independences. So maybe it can be done, but I think it requires something very different, and I don't know. So as far as I know, there are two basically spaces in between. There is the James space, and there are some interpolation spaces due to Pisianshu. And maybe these are more tractable examples, but again, I'm not sure that it's going to be at all easy to understand what happens with those spaces.
On the level of metric spaces, is there a property that's conjectured to be equivalent to martingale type? Like there's...
Yes. So that's kind of one of the big problems in the Riva program. There is a candidate program. Which looks very different. Yeah.
All those applications of Talagrand's inequality to super concentration of first passage percolation and all that stuff. Did you try to think if
a bit, but I think it's actually very interesting in the sense that exactly because, and that was a starting point, to be honest, it wasn't just to do, just an inequality for fun, that this Talagrand's inequality is the kind of inequality that's extremely useful for applications. And in principle, knowing a vector valued version should tell us something more. Now, because of where we are coming from, embeddings was the natural application to look at, but I'm sure that's not the last one somehow. It's clear that there's going to be something else. I don't know of another application, but yeah, that would be very nice.
Any other questions? Remarks? Okay, if there are no questions, let's thank Alex again.
Thank you.
And hope to see you next week.
Sure. Okay.